Just a shout out to Lunar Flu. He's been super helpful. I wanted to share this meeting with people on Hugging Face, and he's been really, really helpful in helping me kind of coordinate these things and share the info up front. So I don't know if you're there, Lunar, but thank you. Now let's get going with the presentation. So today we are going to talk about Gemini 1.5. It's a multimodal, you could say foundation model, or like a really large neural network, which is able to interpret both images and text. And today, the structure of the presentation is going to follow more or less the structure of the paper. So every subsequent slide will be in the same sequence in which the ideas are addressed in the paper. Again, you can pause me at any point and ask questions to me or the group. I think that could be fun. So let's get going. So the most unique or the USP of Gemini 1.5 is that it's really compute efficient. That's one of the things that they mention in the paper. And the second thing is it's multimodal. So even the recent release of Claude 3.0 and GPT-4, these are, and like GPT-4 and GPT-V, these are separate APIs. I think there is some interleaving that happens on the ChatGPT website. But as per Gemini's publication, they are the only large-scale multimodal mixture of experts model, right? So their reasoning engine can interpret audio, video, text, all three. And this thing becomes more and more clear in the evaluation discussion, because every time they evaluate their audio capability with GPT, they need to make a combination of GPT and Whisper, or sometimes I guess for video, the only model they are comparing themselves against is GPT-5, GPT-V, GPT-4V. So that's also kind of a unique proposition of Gemini, which is, it's one of the, I would say, rarest multimodal foundation model. The second big aspect of Gemini is that it can process millions of tokens. And towards the third part of the discussion, I'll get into the main ideas I think help them scale to millions of tokens. But that's really one thing in which they beat both Claude and GPT-4, Claude 2.5 and GPT-4. And the third thing, like I mentioned earlier, the tokens that get into the Gemini 1.45 architecture, they can come from documents, video, and audio. So these three stand out to me as like the biggest value propositions of Gemini. And I'll take a pause here. I think this is the shortest introduction to Gemini I can provide. So if there's any thoughts, questions, I can take it right now.
Thanks for the presentation. One question, is like GPT-4 better in any way than Gemini, or like, is it like Gemini is just better for this?
Sorry, what did you say? Gemini is just?
Or is like Gemini just better than like GPT-4 in every way? Or like, is that yet to be seen?
Yes. So the short answer is yes. And that's what they state in the paper. And let me, actually moving forward 2 slides, that's really another short summary of the paper, is that Gemini 1.5 beats Claude 2.1 on everything. And GPT-4. And so the thing with Claude is that it only works on text. So if I just select text benchmarks, Gemini comes on top, Claude is second, third is GPT-4. And if I choose audio and video, as per the paper, Gemini beats GPT-4 and GPT-4V and Whisper in all tests. So GPT 1.5 Pro, is straight away better than both.
So Shashank, just a heads up. So if you're making a RAG application, then Gemini would be a better choice. Does that mean that?
Yes. Yeah. I think one, from an accuracy point of view, I'll get into details of how they evaluated themselves on documents. So they do make this statement in the paper as well. that for RAG application or for information retrieval and attribution, Gemini is distinctly better than Claude, right? And Claude is better than GPT-4. So that would be my recommendation. The second thing is the context length of Gemini is like insanely larger than Claude and GPT-4, which means you don't even need a vector database, if you're just dealing with small documents. So a lot of the RAG software stack can simplify a lot if you're just calling the Gemini API.
But Shashank, I tested the same prompt with GPT-4 and Gemini 1.5. I think so. It was not Gemini 1.5, whatever they are providing currently on the website. And I understood that GPT-4 was answering much better than Gemini. I observed this. Is it true?
Yes. So I think your observation is must be right. So the thing with the evaluation setups, and I think the first part of this discussion is going to be just about the types of evaluations they do. Even the same for this, like recently Claude came out, right? Claude 2.5 or Claude 3 was released. Like even for Claude, when the same research group or different research groups evaluated the same test on Gemini and Claude, they came up with different results. So the thing is that these benchmarks, like you should take them with a grain of salt. And the benchmarks that I'll show, it's coming from Gemini 1.5 paper. In the real world, you might experience something completely different, right?
But see, Shashank, the way Gemini advertises itself, it's like it's the father of all the AIs out there, of all the large language models out there. But in reality, if we see, GPT-4 outperforms Gemini, right? In terms of providing better results.
Yes. So the thing is that, we have already evaluating, let me kind of answer that by just saying that evaluating these models is really, really hard. I think evaluation of these models is itself a pretty difficult challenge in itself. And the problem is that these models do tons of things. So maybe on one task, one is be better than the other. And in a paper, they might say that on average, we are better. But really for your application, it may not, you should still do your own tests and figure out which API makes more sense for you, right? The paper just tells you at a high level and averages across all tasks, right? So for your specific application or use case, it may not align.
Cool. And just one last question. I just searched your name on LinkedIn. So is your headline as a fractional CTO as a service, a real-time solution for online RL, computer vision and all that?
Yes.
Is it your? Okay, cool. Connecting. Yeah. Thank you. Continue.
All right. So I'll continue from here. And I think we moved those two slides because of that question about comparing Gemini to GPT and Claude. So I hope I answered that question for the person who asked it. This is just like a simple slide talking about the three main applications in which Gemini kind of stands out from the other two models. So one is document question answering. I'll get into the metrics later on in the discussion. Video question answering, which is not possible with Claude, and Gemini outperforms GPT-V on it. And then even in automatic speech recognition, Gemini outperforms a combination of Whisper and GPT-4. So these are the three applications where it stands out. This is now just to give you a good idea of like the simplest introduction to Gemini and the simplest introduction to the applications that you can use it for. And this is a quick background to keep in mind, I think, for the rest of the talk is like why, benchmarks, like I said, designing the right benchmarks is a challenge in itself. And again, what they report, you should take it with a grain of salt and like do your own tests and follow other research groups who are working on better evaluation tools. But one thing that really stands out about Gemini, which is more objective than subjective, is that it supports longer context lengths, right? So the size of the text or video or audio file you can send to Gemini, objectively, you cannot send that much data to GPT or Claude. Now, why is that important, right? And why did these guys work on that? So a quick background of the research in this field is over starting from 1948, when Claude Shannon actually proposed the 2-gram language model, to date, both Anthropic and Google Brain, they have really, accelerated on the context size, or how much of the data can be processed by one model inference, right? And the thing that happens is, as you scale the context size, some of the applications which were impossible before, they suddenly become possible, right? So just keep this in mind, because this, I would say, is one of the biggest strengths of Gemini, right? And on this slide, I'm going to end like the shortest introduction to Gemini. The authors have stated that they saw continued improvement in next token prediction. So again, Gemini is also a language model that can process language. And what they noticed, that up to 10 million tokens, they can send the model to the Gemini API, and it is able to do near perfect retrieval, which is, if I send it a whole book of 10, which results in 10 million tokens, I can find a word in the last sentence of the book, with 99% accuracy. Now, if you compare that to Claude and GPT-4, they don't even support 10 million tokens, right? So Claude 2.1 was at 200K and GPT-4 is at 120K. I know Claude released a new version. I do not know the context length that it supports. But you can see it, Gemini 1.5 beats both of them, by a huge margin. So, so what does that mean? Like, what does it mean to have a longer context length? So in the Gemini paper, they talk about this real world test where they had some data about for a language called Kalaman from Southeast Asia, I think towards east of Indonesia somewhere. And the unique thing about this language is they had like 500 pages of linguistic documentation, a dictionary for this language, and 400 sentences about it. And none of the data about this language was available on the internet. And since this Gemini work comes from Google, again, they train their models possibly on all the data that's on the internet. So testing for them is also pretty hard, right? Because when you're testing, you want to make sure your model hasn't seen something in the training data in order to evaluate it on it, right? So that's why they chose this Kalaman data set, because they also talk about it in the paper. They verified that the Kalaman data was not available in the training data set. And then a simple test that they did was they sent all this material in a single prompt to Gemini and then asked it to translate some sentences from English to Kalaman and reverse. And what they found out was it performed as good. The translation from Gemini was as good as a human translator. Again, I'll get into the numbers later, but I hope this gives you an idea about like why context length matters. Because a use case like this cannot be done with GPT-4, right? You cannot prompt GPT-4 with all this data and then ask it to translate or do any task on that data, right? This is uniquely possible with Gemini. So that's like a quick introduction wrap up about Gemini before I get into the second phase of the discussion. If there are any questions here, I would love to take those, or any thoughts.
Out of curiosity, like, do you have a guess on like how they kind of like got to the 1 million token length thing? Like, do you think they're still using like transformers or something? Or
yeah. So in the third part of the discussion, I'll go into details of how, like from the little information they give in the paper, I think the short answer is they used a sparse mixture of experts model that helped them scale to a 10 million context length. Sadly, that's the only thing they mentioned in the paper, that they use that architecture. They give no information about the loss function. They give no information about the training routine. So it's still kind of a secret sauce of how they were able to kind of jump to 10 million context size. But again, in the third part of the discussion, I'll share with you ideas from different research papers, which I think together explains how they reached the 10 million context size.
Interesting. Thank you.
Shashank, what do you think? This 10 million token size, could it be a marketing gimmick? Like they overhyped this thing, barred a lot, and then it didn't turn out to be the way it should be. So, what are your views on this?
I wouldn't comment. I would just not comment on that question. I don't know, to be honest. And so that's kind of the short answer. I'm going to do my best to present what's given in the paper and talk about other papers that are referenced in this paper. And I think the Gemini group has done a pretty good job in referencing all the related work. So I think studying their papers, studying all these other papers can be used to make an opinion about that question.
Fair enough.
So I think now we'll shift to the second part of the second part of this discussion. So I gave a quick introduction on Gemini. In this phase, I'm going to talk about the evaluation strategies that they follow in the paper and they present in the paper. Again, evaluation is becoming more and more, it's becoming a pretty important part of the research work in foundation models. Because as we just kind of had a discussion about, right, like it's really hard to evaluate and come up with one metric or even like 10 metrics that an applied AI engineer can use to figure out which model to choose, right? But there's a lot of amazing research work happening in this. There's a lot of really good ideas that they talk about in the Gemini 1.5 paper about on how they evaluated things. So I'm going to go deep into these 3 points. And these 3 points are exactly picked up from the paper. So they have broken down their evaluation tests into 3 categories. First is the qualitative evaluations to test for the model's ability to analyze long context size. The second is quantitative evaluations to again evaluate how the model does on long context size. And the third is the quantitative core evaluations, which I would say is not very unique to Gemini, but these evaluation tests can be applied to both, to GPT, Claude, and other models that are out there. But these 2 tests are primarily applicable to Gemini. So we are going to start off with qualitative long context multimodal evaluation. So this, hopefully the next few slides in which I talk about this will give you an idea of how did they make sure that now that Gemini can process long context, what are some real world use cases that become possible, right? And how effective is it in processing long context? So one test that they did was they took the entire code base of the JAX library, which is available on GitHub. And then they asked the Gemini model, they prompted the Gemini model with some questions. For example, this one, like in what file is the backward pass implemented in JAX? And Gemini was able to return the correct answer and also give reference to the exact Python file where that code snippet was available. So I hope this gives a sense that the Gemini model can actually process really long context size because it analyzed like 116 files with like 700,000 tokens, which is already beyond what GPT-4 can analyze. The second qualitative evaluation that they did was they took this book, Les Miserables. Sorry if I'm pronouncing it wrong, but this book had like 1,400 pages, which resulted in 732,000 tokens. And here they are testing the fact that Gemini can process both visual data and textual data. So they gave Gemini the whole book as part of the context, and then they gave a prompt which was a mix of text and images, and the prompt basically asked the Gemini model to identify in which page an event like this was happening, and the model was able to correctly identify the section in the story which relates most to this image, and it also gave the exact page number where it happened. So between this and this, I think they are able to prove that Gemini can process long context and Gemini can work on multimodal data. Those two still just test out image, tests out Gemini on text and images. A third qualitative evaluation that they did was they ran this whole movie, Sherlock Jr. from 1924, which lasts for like around 44 minutes and results in 684,000 tokens. So they sent it in the context to the Gemini model along with a prompt. And they asked the Gemini model to identify the frame that relates most to this piece of text. And the model was able to kind of return accurately the frame in which this information was available, therefore proving that, again, Gemini can analyze long context and Gemini can analyze video data. So that's where the qualitative evaluation ends. If there are any questions, I can take those here before I move on to the next part.
One question. So it seems to be able to generate text and images, but can it also generate video or no?
Yeah. So just one clarification, right? So it can, it cannot generate videos, and it can generate images and text. So you're correct. But the thing is, they don't, this is more of a lookup, right? It's not that this frame was generated by Gemini. It's just that Gemini was able to identify the timestamp in which this frame appeared. So yeah, just to be accurate, they do not show any examples of Gemini generating images or videos, but they do show examples of Gemini generating text, right?
Okay, and I guess it can kind of like listen to audio, but it can't generate audio too.
So again, they do not show any examples of Gemini generating audio. In all of the evaluation tests, Gemini is only generating the text, and this visual that you see, it's like a follow-up step, right? It's like almost a function that, based on this information, is able to pull out the frame. So this is more for reference. This is not the actual output of Gemini. The actual output of Gemini is this.
So it's a text output only.
Yeah.
Okay. Interesting.
So I hope that was a really good question, because I think it's really easy to misunderstand what's happening here. So Gemini is only generating this text, right? And from this text, they are looking up the frame in the video and then showing you that, okay, at 12:01, actually this thing, 12:01, the data in the video actually maps to the prompt.
Gotcha. Thanks.
So now let's move to the second type of test, which is the quantitative long context evaluations. Here, I think before we get in, one concept would be really kind of useful to remind yourself about, or to know if you have not kind of come across it, but there is this concept of perplexity, which you can just think as like, it's a function of the joint probability of seeing a sequence of tokens. So in the perplexity, and perplexity, as you can see, it's the inverse of that joint probability. So the higher the probability of, if a model is not very surprised with seeing a sequence of words, it means the perplexity is low. And that basically means or implies that the model has high probability of seeing that sequence of tokens. So I hope that kind of gives you some idea about this perplexity term. Again, perplexity is inversely proportional to the joint probability, and joint probability over a sequence of tokens or a model just means what's the likelihood that the model has seen that sequence before. This concept will be useful as we get into the quantitative evaluation tests, because it's going to be used in many of the graphs. So one of the first tests or graphs they refer to for the quantitative evaluation is this one. And what's happening here is they are sending documents of longer and longer word length, and then they are measuring the perplexity or the negative log likelihood of observing that document by the Gemini model, right? So as you can see, between Gemini 1.0 and Gemini 1.5, which is the model of discussion in this paper, as the context length increases, Gemini 1.5 still has like lower and lower perplexity. And that's really intuitive, right? Because as the document length, like when you've only seen one word in a document, you'll be more perplexed about it, or the model should be less confident about the second word. But if an AI model has seen, let's say, 500 words in a document, then it should have an easier time guessing the next word. So the fact that this Gemini 1.5 works really well with long context, like if that's the statement that's being made, then the expectation will be that with longer context length, the perplexity should go lower, right? And that's what they observe. And when they compare it to Gemini 1.0, they notice that the perplexity actually shoots up beyond the context size. And Gemini 1.5 also has the advantage that, it has a higher learning capacity, so it can cross even at a 1K context length, where 1.0 does not really shoot up in perplexity. Gemini 1.5 gives a higher log likelihood, to a document of that size. So these are just quantitative metrics that again prove that up to a 1 million context length, Gemini 1.5 can do a really good job at reasoning and other kinds of tasks on a document. Right. And I think here in this chart, this is just an extension. They take the context length all up to 10 million, and they see this really nice behavior that as the document length increases, the perplexity keeps going down, right? And which is what you expect, right? If an AI model has really understood how to process long context length, the perplexity should go down over time. So that's why I think early on in the paper, they make this statement that up to 10 million tokens, Gemini 1.5 does a pretty good job at consuming the context. So any questions still here before I move to the next slide?
Hey, I had a question on so it shows that it's continuing to have the perplexity go down up to 10 million. Is there any sort of hard bound that they talk about at 10 million? Like Gemini 1.0 Pro, it shoots back up after a certain context length. Theoretically, could this perform up to 30 million, or like, did they just stop the context at 10 million, or is that a hard limit?
Yeah. So in the paper, they do not really talk about what's the theoretical limit for the context length. Like they do not clearly, they mention that they use a sparse MoE architecture for the Gemini model, but they do not clearly state how it relates to the longer context length, and they do not make any statements about theoretical limits on the context length, right? So yeah, basically that answer isn't there in the paper. as per my knowledge. And even in the graphs, you can see they just abruptly stop at 10 million. So even if they have something that, continues to go down even for long context size, it's not that info is not available.
Okay. Yeah, I mean, not a big deal. I was just curious if they happen to clarify.
Yeah. I checked that as well. So they don't, and so interesting that especially for code, I think this is just super useful for folks doing applied AI. Like you can see, like for code, like they do not show the context length beyond 1 million for documents. I guess this is English language documents, but for code, they give this perplexity metric up to 10 million, which means it's easier for these models to learn how to write code than how to write English. So after this, I'm going to go into more quantitative evaluation tests that they present in the paper. But I want to kind of also let everyone know that we'll cover a lot of interesting concepts in this discussion. So right now we are in the evaluation part where we talked about perplexity. We are going to talk about needle in a haystack evaluation, and we'll talk about in-context learning. So these two things would also hopefully I'll be able to explain it. And once we are done with evaluation, these are the three concepts in the implementation of an AI model that is my best guess at what helped them reach the 10 million context length. Again, it's my best guess. They don't talk about, the only thing they mention in the paper is that they use a sparse MoE, and I just followed the reference trail of other papers that are referenced in that paper to identify the other concepts that I want to talk about. But we'll be covering these two categories in this discussion. So just a quick intro. Now we're going to go into the second quantitative evaluation test, which is needle in a haystack. So here, I'm going to try and just explain what is the needle in a haystack test before giving you numbers. So in the needle in a haystack test, what is done is in the prompt to the model, you send a haystack. Basically, you send a lot of data, and then in that data, you randomly insert a needle, and a needle is a data point which is kind of irrelevant to the context that surrounds it. And the test for the model is, can it find the needle, which is an irrelevant piece of line or a data point, when surrounded by a lot of other information, right? So that's where kind of the idea comes that this is a needle in a haystack evaluation. And what they do to kind of execute this test on documents is they use essays from Paul Graham, which is available on this link. They concatenate all these essays and repeat them if necessary to reach whatever context length, 1 million, 2 million, 3 million, or 500K, whatever it is. And then somewhere, and then they mention in the paper that at some linear intervals, so, interval 100, 200, 300, something in that order, they insert a new sentence in the essay. And this sentence is, the special magic city number is number. And then they replace the city closure with some random word, and they replace this kind of number closure with some random number. And then they prompt the model with, here is the magic number. And they prompt the model with, here is the magic number, and kind of, they prompt the model with, here is the magic number, and basically test the next word prediction ability of the model to identify the magic number in the input prompt or the input context. And if the model accurately returns the number inside the needle, then it's a success. And if it does not, it's a failure. And let me show the graph, because I think then it will make a lot more sense. So here what's happening is they repeat the Paul Graham essays and concatenate it to create a context length of increasing size, right? So up to 1 million. That's the x-axis. x-axis. So the x-axis is basically a document with longer and longer length by repeating those essays. In every document, they at linear intervals, they place the needle sentence. So what that means is, on the y-axis, you have the 0% and 14% and 29%. So what they do is, at the 14th percentage of the document, whatever number of lines that is, they place the needle sentence. And if the Gemini model is able to respond with the secret number, which is situated at the 14th percentile almost of the document, then it's a success. And if Gemini is not able to return the secret number, then it's a failure, right? So here you can see this red mark basically means that at a context length of approximately 550,000 and at the 29th percentile of the token, when given a prompt that here is the magic number, and there was a needle at that percentile with some number and with some word, the model failed to retrieve that accurate number and basically hallucinated, said something which was not present in the context. So this is the needle in a haystack test. I'll take a pause here, see if there are any questions, because in the next few slides, I'm going to just give you numbers on how this model did on this test.
So I just got one thing. Does that just mean that because there's no red marks in the video haystack and audio haystack that it performed perfectly for those examples?
Yes.
Wow. Okay. All right.
One question. Can you go back to the previous slide? You see but why is it like the special magic city number? Like, what's the city thing?
Yeah. So I'm just quoting it from the paper. I don't know. They don't really give any reasoning for it. I can just kind of show it to you. I know it was weird for me as well. But you can see in the paper, right? Like, we insert in ideally spaced intervals. The special magic city number is number where the city and number are varied for each query. So I don't know why they call it a city, but that's what they say in the paper.
Interesting.
I think that might be because they are giving the number as input and they're expecting the city as output. So I think that is what they're looking for to identify.
No, so I think the test is still to recall the magic number. This is just to kind of create confusion. I mean, from the paper, the city is almost irrelevant. They want the model to return the magic number, right? Or the secret number, whatever it is. Yeah, the magic number.
So in that case, like, what is the query that they're like, just retrieve the magic number? Is that the query?
Yes.
Okay. Yeah.
So this is more, I guess, as like a decoy, how to confuse the model. Yeah, this is basically what they want to retrieve. Interestingly, this is just a side note, but like in the recent Claude release, the Claude 3.0 model, I think, responded with that why is this sentence even here? So yeah, if you guys look up the needle in a haystack test for Claude, you'll see some interesting results. So let me kind of now go deeper into each of these tests: video, audio, and text, starting with text. So they did the text haystack test. Again, Gemini has a context length which GPT-4 Turbo doesn't even support. So that's why you see all these black cells, because they couldn't run the test on GPT. But up till 128 context length, both GPT-4 and Gemini performed perfectly. Right. So this is where I think you should take the tests also with a grain of salt, like, because if both models really perform perfectly, it doesn't help you make any decision or change your thought process. So again, these tests are only as useful as you make them to be. And the other thing that they reported was like beyond 512K token size, they saw 3 failures. And then beyond 2 million, they saw like 2 other failures. Yeah, so this is the text Haystack test. For the second video Haystack test, where it performs perfectly, as you know, we just talked about, right? They like both Gemini 1.5 performs perfectly. So one of the reason is that, you know, the Needle and Haystack test is done on a very specific video. I don't think they're cherry picking these videos, but it's just one video, right? So the video Haystack test was done on the AlphaGo documentary, which lasts for around 3 hours. And you can see here, in one random frame in the documentary, they put this caption or subtitle, whatever you may call it, that the secret word is needle. And also this secret word is needle is repeated, right? So unlike the text Haystack test, they're not even changing the secret word. The same phrase is linearly placed at multiple depths in the video, or basically at, you know, linearly spaced frames in the video. And then what they're prompting Gemini to do is identify, after feeding the video, they ask the model, what is the secret word, right? So, and then in all cases, it answers accurately that it is a needle. And maybe that's why it works perfectly. But again, GPT-4V also performs perfectly, and Gemini 1.5 also performs perfectly on this test. I'll show this audio Haystack test and then I'll take a pause. So in the audio Haystack test, Gemini performs perfectly again, but they found some issues when they ran a combination of Whisper and GPT-4. So the large audio file that they created, the 660 minutes audio file, it was stitched together from the Vox Populi dataset, which is a dataset. I think, again, I could be wrong here, but I think the audio files in this dataset lasts at max for like 30 seconds. And every audio file in this dataset is, comes from a different speaker. So this large audio file contains multiple speakers. And I think at various intervals in the large audio file, like the 22 hours audio file, they put this phrase that the secret keyword is needle, and they put this audio in there, and then they ask both Gemini and GPT-4, what is the secret word? And again, just like the video Haystack test, the secret keyword is not changing, right? So they, at every depth in the longer and longer context, they're inserting the same secret keyword. And then they say that it accurately identifies it. And a quick note on, like, again, to Gemini, you can upload an audio file and give it a text prompt. You cannot do that with GPT-4 Turbo. So at least not when they evaluated it. And so therefore, the thing that they did was they ran the audio file through Whisper, converted it into a transcript, and then sent the transcript to GPT-4 Turbo, and then asked GPT-4 Turbo to find the secret keyword. And looks like GPT-4 Turbo had a lot of failures in finding that out. Again, whether it's because of GPT-4 or whether it's because of Whisper, they do not give a comment about that.
So just a real quick question. So do you think under the hood for Gemini 1.5 Pro, like the way that they're sort of passing through the audio in order to extract the information, would they be using something similar to the Google version of Whisper in order to sort of first do the translation into some transcript and then pass that text into the model, or like, how would that kind of sequence go?
So my best guess would be that they have a single model. They do not have like this combination of two separate models. So they have a unified model that can analyze both audio and text, because there has been some research papers on creating a multimodal mixture of experts, model from Google Brain. So they have a lot of research work on this subject. So that makes me think that they have a single model. But again, they don't give many details in the paper. So
yeah, okay. Thanks. Also, did they mention anything around whether the Whisper is a transcripting model, right? So if they just give the script to GPT-4, if this random sentence is missing from the GPT-4's input, obviously GPT-4 cannot find it correctly, right? So did they mention anything about the output of Whisper, whether it actually contained that secret or not?
Sorry, I didn't hear the last part. If it actually contains
the secret keyword, the Whisper
yes. Yeah, they don't give information about that. So again, they don't attribute whether it was a failure of Whisper or GPT-4. They do not mention that. It could be a mistake in the transcription. I think that, again, it's my guess that it could be a mistake in the transcription step that led to this failures, because GPT-4 Turbo it can surely identify a secret keyword, right? Because this is within the context length of GPT-4 Turbo.
Yeah.
Also on the also on the page 22, they have explicitly mentioned that Gemini 1.5 Pro is a generalist model over USM and Whisper. So I think it is processing both text and audio files with the same model.
Yeah. And also from a cost efficiency, it wouldn't make sense that, because it's cheaper than GPT-4 today, it wouldn't make sense that they're running multiple models. So I think now let's move to the next part, which is the quantitative long context evaluation. So, actually, we are on the same part. We just covered needle in a haystack test. I hope that's pretty clear. That test is clear. You will see that test being applied to Claude, and I'm sure all the new models that are going to come out. The other evaluation test that they talk about in the paper is the MTOB test, which is machine translation from one book benchmark, first discussed in this paper. And what this test does is it measures the ability to learn sentence level translation between these two languages, right? And the reason why this test really makes a lot of sense is because Gemini is trained on a lot of the web data. So any other, if it's not an uncommon language, Gemini has probably already seen that language before. So they do this really nice thing where they first evaluate all three models on zero-shot inference, which means they give no information to the model about the language, and then just ask it to translate from English, from Kalaman to English, and then English to Kalaman, right? So if the accuracy was higher than this, right? If the accuracy was, let's say, in the 4, 0 to 6 is the scale. So if it's on the higher side at zero-shot, it would basically mean that the training data for Gemini already has information about Kalaman. And that would be wrong, because then the advantage, at least, since they talk, this is the test to evaluate the ability of the model to analyze long context. And it's not a test to evaluate how big the training data was. So it would be wrong if Gemini used, tested itself on test data, which was already part of its training. So by just looking at these numbers, it's very clear that whatever references to Kalaman was available to Gemini was also available to GPT-4. And Claude in zero-shot actually performs worse than both. So whatever training data set that Claude 2.1 is trained on, it has far fewer references to Kalaman. So that's why they do this zero-shot evaluation. And then what they did was they asked a human language learner who actually, went through all the documents and knows the Kalaman language to score how well did Gemini perform in translating between these two languages, between 0 to 6. And then they compared Gemini to Claude and GPT-4. And as you can clearly see, right, for the half book inference, again, because Gemini has a longer context length, you cannot even send the full book to Claude and GPT-4. Even on the half book test, Gemini outperforms significantly GPT-4, and Claude 2.1 comes out in the second position. So that's the MTOB test. By now, we have covered both needle in a haystack test and MTOB test. Both are quantitative long context evaluations. Now we are going to get into the AIS test. If there are any questions here, I can take those before I jump to a new concept.
Slight question, but how did they score the human language learner? Like 5.52 and 5.6.
This number?
Yeah.
Yeah, so they had a human language learner score the translation.
So like one of the human language learners make the translation, the other people score it.
Yes.
Okay.
Yeah, and like I say, right, this language has at least 200 speakers in the world, right? So they probably found one of them and use that person to score the AI model.
Gotcha. And yeah, kind of like, I know dataset contamination is like a huge problem with large language models. So this evaluation is interesting.
Yeah. That's why this test is really, really kind of a good test, for these models. There is no training data contamination. So let's move to the next test that they use, which is called attributable to identify sources protocol. So in this test, they feed both Claude and Gemini this particular book, which has 710,000 words. And then to kind of both the models, they send these 100 questions. And then there is a criteria, like a very unique criteria to evaluate the response of the model. So, and the unique criteria is that for each of the 100 questions, whatever answer the model gives you, the model should give you the premise for the answer right after it gives you the answer, right? And it tries, basically it's trying to make sure that the model does not just give you the answer, but it also attributes the answer to the question with where, like which part of the book is the answer found in. So it's a pretty good test that way, right? Because like, especially for many of our use cases, right? Applied AI use cases, you don't want to just give the answer to the user from a PDF or a document. You also want to show the user where exactly did the AI model pick it up from. So to evaluate models on that criteria, this test comes really handy, right? And what they found out was, again, even if they limit to the 4,000 token context length, Gemini 1.5 significantly outperforms Claude, right? So I think this was a question in the earlier part of the discussion that like, is Gemini just better than Claude, right? So at least in this test, there is a huge difference between what Gemini does and what Claude does, right? And also the other thing you can see is that answers from Gemini are much more succinct, right? It's much shorter. It's not like giving you too much information unnecessarily. Like Gemini is able to give a shorter answer, which is more relatable. But what is true, like what was good about the MTOB test is that there was no cross data contamination. Like the test data was more or less never seen in the training data. What you can see here is in the zero shot test case, Gemini actually performs really, really well. And so does Claude. Like Claude also does a pretty decent job. which means Claude is able to remember some facts about this book from its original training data set. It doesn't even need the context, the book to be uploaded along with the prompt in order to answer it accurately. But like Gemini, even with zero shot, does really well. So there is training data and test data contamination that's happening in this test. Just something to keep in mind.
Actually, I'm just noticing one thing here. The 1.0 zero shot versus a 1.0 4K, it's actually zero shot that's actually better, right? And it's almost as equal to 1.5's smaller context, right? Is that because this essay is already present in the internet?
Yes, yeah. So this is the zero shot case, right? Because it's when you just ask a question about less miserables and you don't give the book, then both of them perform. Yeah, this actually performs better. That's a pretty interesting observation. So,
and better than the 1.5 with some context too.
Right.
Very bit.
And it's shorter. So, yeah.
Okay.
Yeah. Solid observation. I mean, I guess it's just because 1.5 knows a lot more.
Do they have to prompt the model to give the response in the right format that they're looking for whatever metric they're using to, evaluate it? Or are they just seeing whatever comes back as just kind of the raw evaluable, metric?
Yeah. So, they just make one comment. So they just say they create a set of 100 questions and they have given this as a reference. Maybe there are details about how these questions are framed. And they do mention here that for the longer context length, they need to resolve some expressions. Like they cannot just say the sibling, the protagonist. Maybe they need to name the protagonist. So they have admitted they had to do some modifications to the question when they gave the whole book versus 4K. Yeah. So, yeah, I think you just check out this reference number. That will give.
Yeah, I'll do that. I guess I was, what caught my attention was because I don't know if it would innately, by default, give the exact, page number that it got some piece of information from, unless it maybe was specifically asked. In your response, be sure to cite exactly kind of which frame it came from or which page it came from or something like that. Seems to need to be included.
Yeah, I think for that, you'll definitely need to structure the prompt. But here, just to be clear, right, it's not that the AIS metric is not evaluating on the page number, but it just expects that it just expects that the premise, right? Whichever page the answer is available in, and whichever paragraph the answer is available in, you should at least pick one sentence and follow up the answer with that sentence.
Yeah, right.
Yeah. So even if it doesn't give the page number in the premise, you at least need to quote something from the book. So that's what is special about this attributable to identified sources test. And they do something super interesting here. Again, this is the column to study because this auto AIS, what they're doing is here they use human evaluators to evaluate the responses. So the human evaluator says that the premise was actually present after the answer. In this column, the scoring is not done by human evaluators, but they use Gemini 1.5 Pro itself to score how well Claude or Gemini 1.5 Pro does, which was rather confusing for me. So, it didn't make a lot of sense, but I'm just calling it out. So when you study the numbers, I would recommend, only look at this. So here they state auto AIS uses Gemini 1.0 Pro as the judge. So I think we are going to now finish up the quantitative tests in the next 2 slides. So the final, actually here is where the quantitative tests for long context evaluation ends. These are the I would say really useful ideas that I picked up from the paper. After this, we go into the third part. Like I mentioned here, there are 3 ways they evaluate the model: qualitative, which we covered; quantitative, which we have now covered completely. Now we are going to get into quantitative core evaluation tests. So let's get there. Yeah. So, I mean, there is no real, I would say, there is one key difference between a quantitative core evaluation versus a quantitative long context evaluation. And the key difference is that these tests are designed not to evaluate how well the model performs on long context size. They are designed more to, more to evaluate the model on like everyday tasks. I mean, not everyday tasks, but like common use cases that other models like Whisper and USM also can, solve. And that's why I've it's available under the core evaluation tests. So to understand this table and understand how Gemini does on audio data, there are 2 metrics to really know about. One is the word error rate. A word error rate in the context of an audio file is pretty simple to understand. It basically says that when you're transcribing an audio file into text, after transcription, just calculate the fraction of words which have been incorrectly transcribed. So if there is a word in the audio which was missed, then that's an error count of 1. And similarly, if there was a word in the audio which was transcribed incorrectly, right? Like tree was transcribed as plant or something other mistake like that, then the error count goes up, right? So now to make sense of this table, what this table basically means is that on the data set that they analyzed it on, Gemini 1.5 Pro, only for 5.6% of the words it made a mistake, versus Whisper made a mistake on 7.3% of the words present in the audio file. So it's a very simple metric to understand, and I would say easy to interpret. The second metric for audio evaluation is BLEU, BLEU, and this metric is useful not for audio transcription but for speech recognition and speech translation. So in this, it's possible, basically what BLEU allows the test to be is like it allows the test to handle cases where there can be multiple ways to interpret the audio, especially in the case of speech translation, right? When you go from one language to another. And again, in the case of speech translation, they use this cohost 2 dataset, which is a dataset of 20 languages. And when you translate those 20 languages to English, there may not be just like one correct English word for that word in the other language. So in the case of BLEU, the word error rate will be really, really high if I use WER here. But in the case of BLEU, what they do is they break down the output data into chunks or phrases, which are typically 4 gram or 4 words. And then they get a human evaluator to test whether that 4-word phrase accurately represents the audio which came in a different language. So a 4-word phrase said in a different language, when transcribed to English language, do they more or less have the same meaning? And that judgment is given to a human, and that's how they calculate this metric. So as you understand, it's less strict than the word error rate metric. Any questions here?
do they use like a prompt for Gemini, like to translate what this says, like for audio?
Yes. So they use a prompt for both Gemini, like Whisper only does transcription, so there is no prompt, but for both Gemini Pro and Ultra, they give a prompt. They ask the model to translate from a particular language to English.
Okay, thank you.
So now this is kind of the second set of core evaluation tests. I'm not going to get into the metrics for these tests, primarily because we don't compare the model to Claude or GPT-4. Even though those numbers are available online, if you search for Gemini 1.5 versus GPT-4, you will find metrics on HelaSwag, MMLU, and many of these other evaluations. But for some reason in the paper, they only compare, like you can see it here, they only compare GPT 1.5 to, they only compare Gemini 1.5 to Gemini 1.0. They don't even compare to GPT or Claude. So I'm not going to go into details about it. But I do mention that these core evaluation tests are really the most important ones when figuring out which model to use, because they cover the more common use cases that users have. Like most commonly, people have some maths and science questions, some coding questions, some multilingual questions, and instruction following prompts. And these things, the capability of a model to do well on these tasks is evaluated in these tests. Like none of the other tests that we talked about evaluates the model on reasoning, coding, and instruction following. So these benchmarks are really, really useful. But again, because they didn't give any numbers, I don't have any numbers to show here. And this is where the evaluation section ends for the discussion. And we are going to now move to the more interesting part, which is, but how, right? Gemini 1.5 clearly does better than Claude and GPT-4, but how does it do it, right? So I think some of you already asked that question, like, is it a unified model or is it just a combination of Whisper plus GPT-4, right? A similar setup like that. So in the next part, I'll go into, so we'll start the research trail from one of the statements that's made in the paper, which is like our first point of evidence. And then we'll, then I'll take you through the other ideas, other related ideas that will hopefully answer the question for you. How does Gemini do it? Yeah. So I hope this is going to be interesting. If there,
Shank,
yeah, right.
This is not related to AI, but the thing is that in this paper, Gemini seems to win at every aspect than GPT-4, right? So could there be a bias of Google in making this paper? I mean, isn't it sketchy that Google is winning over each and every, thing that they show?
So your question is that it's beating GPT on every benchmark?
Yeah, so could there be a bias of Google in creating this paper? I mean, there might be aspects, right, where GPT-4 is winning, right?
Yeah, and so, so what I would say is, firstly, these evaluation tests are not really very objective, right? The way the tests, it's like these are essentially metrics, right? These are not goals, and like metrics are designed to evaluate, whoever designs the metrics has some idea in mind. So they are not, I wouldn't take them objectively. So even if Gemini performs really well on all the benchmarks, I think they, like I also am not an expert like the authors of this paper, but I don't think they give reports, they give all the data files. So I think they are very honest in kind of giving us the metrics. But when you have to make a choice for the model you want to use for your application, I think you might want to go even further. You want to evaluate these models on benchmarks that are not mentioned in this paper.
Okay. Yeah.
That's my kind of point of view.
Yeah, fair enough.
Cool. So now we'll dive deep into some ideas about implementing a model like Gemini, and possibly this will give you some ideas about how they implemented the Gemini model and how they trained the Gemini model. And I basically kind of distill down the core ideas into 3 categories. So the first idea that we are going to talk about is the sparse mixture of expert architecture. The second idea is going to be gating structure, and I think it will make more sense when I, go in a particular order. But these are the 3 key ideas I'm going to communicate in the rest of the discussion, and hopefully that will make you feel more confident about training a model like Gemini with whatever infra you have available. So there are 2 information about the secret sauce that they have. They have mentioned in the paper that, okay, this is why Gemini 1.5 Pro possibly beats the other models. One thing they mention is definitely the infra that's available to Google. They have trained the model on 4096 GPU chips, TPU chips, TPU accelerators. It's Google's custom AI accelerator. So they train the model on 4096 such chips, which is distributed across multiple data centers. I don't even know how much RAM or how much GPU RAM or TPU RAM each of these accelerator has, but I'm sure it's plenty. So their data and their compute infra is, I would say, a big part of the secret sauce. The other factor is that they are training on multimodal and multilingual data. Again, because it's Google, they probably have access to the largest data sets in multiple languages and have access to multiple, the same information in multimodality. Like they have a caption, image, audio file, video file, everything available at their disposal. So the data set, the data center, I think are 2 key pieces which explain why they achieved what they achieved. The other thing they mention is they pre-trained the model on web documents and code which incorporated images, audios, and video content. That's the other thing which is very special about Google. Beyond pre-training and training, they also did instruction tuning of the model, which is basically training the model on a preference data set. And here possibly they have used some reinforcement learning techniques or some direct parameter adjustments based on some feedback, right? Based on some loss functions that they have designed, particularly for this fine-tuning phase. They do not give away any details about this instruction tuning phase. The only thing they mention is that they do it, right? So these 3 together, I think are pretty critical. Were pretty critical in helping Gemini achieve the benchmarks that it did. Yeah, and I think all these 3 things are very special about Google, something we cannot replicate, or any normal smaller organization cannot really replicate any of these strengths. So I'm just putting it out here, and we'll go deeper into some other ideas that, we can actually find some open source support for. But if there are any questions till this point, let me know, because I think after this we dive deep into mixture of experts architecture, which will be kind of a detour from the current tone of the discussion.
So actually, quick question. Sorry. The reinforcement learning part, that is for the instruction tuning, right? Just a general question: do they involve the reinforcement learning parts of the model in the actual model itself, or do they separate out that thing? Sorry, hope you understood. So for the instruction tuning phase, you mentioned that this could have some reinforcement learning based approach, right? So this reinforcement learning part of the model, is it included in the actual model, or do they generally separate them out? This is a general question, not specific to the Gemini.
Yeah. So the reinforcement learning phase, when applied, it's done post training, right? But it is applied on the same model, and generally between pre-training and training, the loss functions slightly change, can be a little different, but both training and pre-training, the loss functions are, in reinforcement learning, basically you work on feedback and not loss functions, really, not the kind of loss function evaluation that happens in training. So it's starkly different, right? Like the training strategy is starkly different when you do reinforcement learning, but the model.
Right. Okay, the model. So the second part of the model will be is part of the Gemini model.
Correct. It's the same model, right? So it's the same model weights. So first you take the architecture, you do the pre-training on the pre-training data set with a specific set of loss functions. Then you move the model. You don't move the model, then you kind of train the model on a larger data set, maybe with slightly different loss functions. The pre-training objective can be different from your target objectives that you have for the model. That's how the pre-training and training differ. And same thing is true for reinforcement learning, right? Here, as you see, like I mentioned, the goal of the reinforcement learning phase is not the feedback that's designed. It doesn't completely capture the things you want to train the model on, but it tries to almost like fine-tune the model to fine-tune the model's responses on certain characteristics, right? Like naturalness and coherence. So
okay, it's like if I understand correctly, maybe correct me if I'm wrong. It's like basically different optimization or different strategy to train the same model of the same set of parameters.
Yes.
Okay. Yeah, I think that makes a lot of sense. Thanks.
Yeah. So I think from here onwards, we are going to move to a completely different tone. I think after this slide, it's going to be less and less about Gemini and more about the mixture of experts architecture. So, and the reason, and basically the fact that Gemini 1.5 Pro is a sparse mixture of expert transformer-based model is the only information that they have given about the implementation of this AI model. Otherwise, most of the paper is about evaluation and what evaluation tests they ran and how they deploy the model. They say very little about what the actual model is, except that it's a sparse MoE. So I'm going to take that single evidence and hopefully introduce you to many research papers from Google Brain or from related labs that have done work on MoE. And hopefully that will give you a clear idea of what does it take to train an MoE model. And MoE is like a big part of the secret sauce behind creating a model like Gemini. So it should be useful for you as well if you're planning to train or understand these models, like understand these really large foundation models. So maybe I'll start off with the transformer architecture. I don't know. Let me see where I have that. Yeah, I'll start off with the discussion with this slide because I think most of you know what a standard visual transformer architecture is. And then I'll take you, then I'll introduce ideas to explain how the MoE architecture differs from the standard transformer architecture. I think that would be the easiest way to introduce it instead of going deep into MoE. And please, ask me to pause wherever you want. I can go deeper into any aspect. But a quick summary on how visual transformers work is you you have any type of input data, whether it's images or text, you tokenize them you tokenize the words and the images into small patches. And then each of the patch is linearly projected through a fully connected layer into an embedding. And then you combine the projection and the positioning embedding into a single vector. And then what you have now is a sequence of vectors, right? So you can start off with the image, or you can start off with a sentence of words. In both cases, you run through the linear projection and end up with the sequence of embeddings or vectors. And the transformer architecture basically says that run through these tokens through a set of stacked transformers. And internally, the transformer looks like this, where the first embedded patches run through a norm. Then it runs through a multi-head attention layer, which I've kind of showed in 3D here. It's not super important for you to grasp what's happening here for the rest of the discussion, but this is more of a refresher on what transformers look like. And after going through the multi-head attention, so this whole thing is sort of acting like a dropout, where the initial projection is forwarded to this addition layer, and the input is also passed through the multi-head attention. And then once you have kind of combined both the vectors at this point, you run it through another norm layer and an MLP layer, then combine them again. And then such encoders are stacked one over the other. And at the end, you get your output embedding. So in this 3D figure, pretty sure I'm not wrong, the flow is like this. This is your input embedding. This is the multi-head attention layer. And then these are your outputs, which come out at this point. So the transformer encoder basically allows you to start off with human interpretable data, and it encodes all of that into a sequence of vectors. And a lot of research publications since the last 4 or 5 years have already talked about it. These encodings are really useful for many different tasks like image classification, image recognition, audio transcription, and many more. But this is the standard visual transformer. Some modifications to this is what creates the mixture of experts model. So I'll take a pause here, see if there are any questions, and then go deeper into MO. Nice. Good. So, feel free to stop me at any point. So let's look at this MoE architecture. So the key difference between MoE versus the standard transformer is, in the case of a transformer, whatever comes as input, it is directly sent to the next layer, which could be, and I'll go into details of what exactly that is, but it's directly sent to the next fully connected layer or the next encoder. In the case of a sparse mixture of expert, what happens is you send the input to a gate, and the gate acts as a router, which sends only a fraction of the input data to subsequent layers. That's the easiest way to think about it, which is like MoE models have a learned routing function in between, which directs inputs to a subset of the model's parameter. So unlike dense transformer model, where the input flops, right, the input operations basically pass on layer after layer completely. In the case of MoE, only a fraction of the inputs are passed along to subsequent layers. That's like a short intro on MoE. Why is it useful? So let me give you kind of some background on that. So the vision for MoE is, how can you train a single model that can do thousands of things, right? Which can do well on a variety of tasks. So whether it's translation from one language to another, whether it's coding in Python or C++, whether it's like doing image classification, how can one train a single AI model which is good in all these tasks, right? And dense transformers, if you feed more and more data to it, right, to do a lot of different variety of tasks, it becomes really inefficient to train them, right? Computationally, it becomes cost prohibitive. You need a lot more GPUs. And even if you can somehow train this model on a lot of different modalities, because you need to increase the learning capacity of the dense transformer, even if you can do the training at inference time, you will see that it takes a lot of time, right? Even for the small task. So let's say you have a dense transformer that you have trained on both images and audio. Just because at training time, you need to feed it more data, it implies that it has more parameters than a model which is just trained on text or just trained on audio. So now, because this multimodal architecture has more parameters, it's going to be slower during inference time, right? So that's kind of the biggest pain point in taking a dense transformer and just like training it on a lot of modalities. And like in search of that solution is where researchers found out about this mixture of experts idea. And there are some notable works on this topic. There is the switch transformers paper, which introduced the idea. There is this beyond distillation paper, which talks about how to use a mixture of experts model to almost route at a task level. I do a better job in explaining what it means to route at a task level, but basically they train one model to do multiple tasks. Exactly what Gemini does. Gemini performs multiple tasks. They also, in this paper, GLAM, they talk about how can you scale or make larger and larger language models using the mixture of experts idea. And then the final paper, which I will just reference here, is scaling vision with sparse mixture of experts. In this paper, they talk about how do you scale a vision model, keep adding parameters to it, and still kind of make it do a good job in reasoning on visual data. So this is kind of a quick intro on why mixture of experts models are used. Next, I'm going to contrast the mixture of experts model to Ensemble Model, which is a related idea but works very differently. So I'm sure some of you probably have heard of an ensemble model. So in the ensemble model, the way the data flow works is you have your data, you copy the data to 4 different algorithms, and you get 4 different solutions. And then you blend all the solutions to create one response. The idea behind an ensemble model is that a bunch of weak learners together can perform well, right? Here, the thing to note is that the data is copied to each and every weak learner, which is very different from how mixture of experts works, right? So in a mixture of experts architecture, what happens is the first thing is your gating network. So whatever input data you have, and this is your equivalent to the ensemble models in a mixture of experts model. So this is your collection of experts. This is your gate, and this is your initial encoder. So once you've encoded your data through your first dense block, the gating network routes some fraction of the data to one expert, another fraction of data to another expert, and another fraction of data to another expert. So the same expert or the same model is not observing all of the data. That's the key distinction between mixture of experts and ensemble. Here you can see the same learner, the same model actually consumes all of the data. Just kind of quickly in here so that you won't spend time.
Sorry, one question here. So are you saying that in a mixture of experts, each expert doesn't have like the full context? It's like they have like specialized token for each of them that were sent by the gating.
Yes.
Okay.
That's correct.
Just a quick question. Can we get a recording of this session? Because I got a need for something urgent.
Yes. Yeah, sure. This meeting is being recorded, so I'll post it on the Hugging Face channel, and you can pick it up from there.
Okay, sure. Thank you.
So, oh no. Okay, let me pick from here. So, yeah. So this is. Let me actually answer that. I have one slide dedicated to that question as well that you just asked. Yeah. So, yeah. So, I mean, the same question that you just asked right now, right? Like, wouldn't having n different experts who are sent, and every expert model is being sent a different fraction of the input data. Like, by doing that, isn't that a disadvantage? Because now every expert needs to separately learn basic reasoning, basic logic, and basic common world language knowledge. Because in the ensemble case, you're sending all the data through all the models. So each of the experts in an ensemble model gets to see everything in your training data, right? So there is no loss of information. But in mixture of experts, you're only sending a fraction of the observed data to an expert. And intuitively, it does make sense that it's going to perform worse. But in the switch transformer paper, what they clearly showed was a mixture of experts architecture performs significantly better than a dense transformer architecture. And they showed this by using this chart. And again, this chart uses the perplexity concept that we have already covered. So in this chart, what's happening is they are showing the perplexity of the models, the perplexity of the model in observing the training data over subsequent training steps. So as we talked about, the lower the perplexity, the higher the likelihood that the model has already seen that information. So at a perplexity of minus 1.6, it takes the MoE model only, almost like 0.6 training steps. So in 0.6 training steps, an MoE model is able to reach 1.6 perplexity, minus 1.6 perplexity, while a T5 dense transformer model needs to be trained, for 2.4 training steps, which basically proves that it's more efficient, both from a cost and energy point of view, to train an MoE model versus a dense transformer model. There's a 5x reduction in the training steps to reach that, 1.6 perplexity.
So is there a mechanism at all in the architecture for different experts to sort of combine their learned knowledge about the information in order to get more sort of deeper understandings, kind of like in a convolutional neural network, how it can combine lower level features sort of, more shallow into the network and then higher level representations deeper in the network? Is it anything sort of like that or not?
Yeah. So it's not, so I think you're talking about feature pyramid networks, right? Like pyramid architectures or UNets. So those architecture ideas that are useful in convolution, those ideas can also be utilized when training an MoE model. The switch MoE model, and so the MoE idea, the mixture of experts architecture design, can be applied to an LSTM. It can be applied to a transformer. Those are the two examples that I've come across. But you can actually apply the MoE idea to a UNet architecture or a feature pyramid network as well. And yes, I think there are some design decisions that researchers have made, which helps the MoE architecture to learn to observe the data at different levels of abstraction, right? Both at a high level and low level. So the short answer is yes. It may not directly relate to how those ideas exist in convolution networks or UNets, but they are related at a high level. So one intuition that might really help is, and let me kind of show you one architecture. I think that will help give you a picture of how a mixture of experts model is different from a standard transformer model. So the standard transformer model, right, as you can see here, you run the embedded patches through a norm, then through a multi-head attention, and then again through a norm, and then through a MLP. So in a mixture of network architecture, you replace the MLP with a MoE design. And what is an MoE design, right? So here you can see it. It just like replaced this layer with an MoE, which is this, right? And what's happening here is after your self-attention and after your add plus normalize, basically after this and this, instead of sending all the data after the add plus normalize step to a fully connected layer, you send the data to a router. And this router, and I'll explain how it kind of operates, the router is basically just a dot product between the vectors that are coming out of the add plus normalize step and some trainable parameters, an FC layer, which represents the router. So it's just a dot product between an FC layer and the output embeddings of this layer. And the dot product basically is used to route the input embeddings to one of many FC layers, right? So in a standard transformer, you have just one FC layer. In a MoE architecture, when applied to a transformer design, you have multiple parallel FC layers, and the router decides when an embedding is sent, like which embedding is sent to which FC layer, right? And I've mentioned here, which is picked up from this paper, that one way to think about it is that it's almost like a dropout, right? So if your layer, right, if your MoE layer is just like a single fully connected layer, it's almost acting like a dropout, right? So some of the embeddings are not going to run through, let's say, this MoE layer, which basically, right, it's almost like a dropout condition where even in dropout, you don't pass all the vectors through a FC layer if some threshold is not crossed. So that's kind of the idea. And there is always a dropout ratio also applied in an MoE layer. So some fraction of the embeddings, they don't go through any of the experts. And then some fraction of the embeddings go to one of many experts that the router chooses. I hope this gives some intuition, and like understanding this is going to be very critical in understanding, why MoEs work. Let me go through one or two slides. Maybe that gives better intuition. So, like I said, since I've introduced the MoE idea, we are now drifting away and away from Gemini, like the core Gemini paper. And the Gemini paper talks about the fact that Gemini is based on mixture of experts architecture. And in these slides, I'm going to just introduce you to different research publications that probably on which the Gemini training and architecture is based on. One of these papers is called the Multimodal Learning with Linear Language Image Mixture of Experts. So in this paper, they have this visualization where they show how to train an MoE model on different modalities, right? So if you have a text modality and image modality, you can just look up the text data using byte pair encoding or any other encoding schemes. You can project the tiles in an image through a projection layer and end up with embeddings. And once you have any of these two sequences, then you pass the sequences through a dense encoder layer, which could be a transformer. And after that, you pass it through a self-attention layer, which is similar to the standard transformer design. And after that, the output of the self-attention is sent to a router, right? So again, in traditional, here I think I have it after this. In traditional transformers, there is only one MLP layer inside every encoder. In these MoE transformers, as they talk about in these papers, there are multiple MLP layers. right? And the router is basically choosing which token, right? So if you have a sequence of, let's say, 20 tokens here, after the self-attention, you'll again have 20 tokens. Each token is sent to the router, and the router decides which MLP to send the token to, right? The sum of tokens that is sent to all the experts here, every MLP is like an expert. So the sum of all the tokens that is sent across to all MLPs is equal to the token length after this layer, right? The only reason that's important, I'm mentioning it, is to understand that the input size to each of the experts is smaller than the input size to the router. And it will help you to kind of understand that's the key difference between an MoE design and an ensemble model design, right? That's where the sparsification also happens. And that's why they are sparse, because it's not that you are copying over the output of the router to each of the experts. You are selecting a fraction of the dimensions and only sending one fraction to one expert. And once you have the output concatenated across all the experts, you can do something like an average pooling or any other sigmoid layer or any other kind of layer which combines all their output. In this paper, that's what they do. They do average pooling, and then they calculate a contrastive loss to reduce the distance between a text which has the same meaning to an image which has the same meaning. So like the word bird, the output embedding of the word bird and the output embedding of the image of a bird, both of those embeddings will be the same after the contrastive loss training. That's what they achieve in this paper. And and this is exactly what Gemini is able to do as well, right? Gemini is able to consume both images, text, even audio and video, and map it to some embedding space where it can do reasoning on those data points, independent of in which form it comes, right? So if you remember the initial qualitative test, right, where it's able to take an image, visual description of what's happening in a book, and it's able to relate that visual sketch of what's happening in one page of the book, and it's able to relate that to that particular page in the book. It's able to do that because it's mapping both the image, the input image, and the text from the book to the same embedding space. And very likely they must have taken ideas from this research work because it also comes from Google. The next two visuals will give you some intuition on why these, like, what are these experts really doing? So they have this H14 architecture, which just means that a mixture of experts where they have 14 experts in the model or 14 MLP layers. And what they notice is at the 18th encoder block, and like to refresh your memory, right, like the transformer encoder blocks are stacked on top of another. So at the 18th block, when they looked at which original image patches were routed to which experts, and when they analyzed it over a batch, what they saw was that patches of plants, doesn't matter whether that patch was, that plant patch, which image it was appearing in, like all plant patches across multiple images in the batch, they were all being routed to the same expert, right? And then they saw that this natural grouping of the semantic information in an image patch to a particular expert was happening post-training of the MoE model, right? Which makes it more relatable, I think, to how also we operate and as how humans operate, right? Like we become an expert in something, and a human expert on one topic can do a better job at analyzing data from a particular domain than another human who is an expert on something else. And they kind of almost see the same behavior in the MoE architecture. The same thing is also true when they break down the routing based on modality. So what they saw was that expert 1 or MLP layer 1 was routed mostly text patches or text information, versus expert 8 was routed mostly image information. So it's not just that within a modality, the experts are becoming good at a particular domain. The experts are also specializing for a modality. So they observed both of these patterns in the MoE models that they trained in this paper. And I think this idea contributes heavily to how they were able to, like, this idea has influence on how Gemini is able to, crack the puzzle of being a multimodal foundation model, while Claude and GPT are not able to do so. So I'll take a pause here, see if there are any questions, and then I'll briefly talk about these results.
You may have covered this just before and I may have missed it, but how does that router sort of, I don't know, decide what part of the input data goes to which, like MLP in that diagram, for example? How is that distributed?
Yeah. So yeah, I've not covered that. I'd be happy to explain that quickly. So this is a simple example. So your question basically relates to how does the gate work, right? And the router and the gate are the same exact thing. So once you get the input embedding of an image or a combination of an image and a text, remember Gemini can, in the same prompt, Gemini can take as input an image, a text, and even an audio file. So even if you give data in multiple modalities, the first dense transformer encoder maps everything to a sequence of tokens. And therefore, you are going to end up with a really long token, right? Because you're combining an audio file, an image, and a text together. So that really long token is now sent, a really long sequence is sent to a gating network. And then the gating network needs to decide to which expert will it send the information. So the way the gate works is that it does a simple dot product. This gate is a fully connected network. The X is a vector, right? So, and the parameters in the gating network are trainable. So when you're training the model on image and caption pairs, or text to text tasks or image to text tasks, whatever combination of modalities it might be, during training, when you have those input and output pairs, the parameters in the gating network are modified, or back propagation runs through them, so that the parameters in the gating network tend to select a sequence of numbers. And when you take the dot product of the sequence of numbers in the gating network to an embedding vector, right? And remember, like when you send different modalities, it'll be easier if I actually just draw here. So once you have, let's say, a lot of different data points, where the first 3 data points are about images, the first 3 are about images, the last 3 are about text, and each of these data points is a vector in itself. During the back propagation step, they initialize the gating network with some random parameters, and then they take a dot product of the embedding vector of this data point with a particular FC layer, and they calculate this router scores matrix, right? So in the router scores matrix, which comes from this FC layer, every expert is given a score on kind of the likelihood that the router will pass on that token to that expert, right? So it's a simple dot product, and after it gets the score, it's normalized. And once it's normalized, they use a simple gating scheme called the top K gating scheme, which just means that the experts, the top K experts for a particular token, whichever, the top K experts with the highest scores for a token, the router sends the tokens embedding only to those experts. So I hope that answers the question.
Yeah, it does. That was a really good explanation. Thanks.
Oh, it sends to a top K expert? So not just one expert. I guess it's routing each token.
Yes. So every token is routed to a separate expert, possibly. Right. So Yeah.
Okay, but one token goes to one expert.
Correct.
Yeah.
And so that's what happens in the Swiss transformers paper. Like I mentioned here, now there are multiple, you'll find multiple publications on mixture of experts. Even Mistral, the organization which open sourced their foundational language model, their model is also based on a mixture of experts architecture. So this architecture is becoming more and more popular. So you'll find a lot of publications talking about it. All the papers that I looked at, all of them do token-based routing. So a token is only, the routing happens at a token level. But this particular paper which also comes from Google Brain, they do route things at task level. So based on the prompt, it selects a unique expert. So this visualization is from that paper, Beyond Distillation, where they talk about task level routing. Here I'm showing you token level routing and it just gives a good intuition about how the whole system works. So let's say that you get a same prompt with Mandarin and English tokens, both included. The way the mixture of experts idea comes really handy is, even though you have sent both languages in the same prompt, the router can have a higher weight of sending a Mandarin token to an expert which specializes in Mandarin, and like English token to an expert which specializes in English, right? So the individual experts, which are just FC layers, they can operate on the embedding vector. They can apply different kind of matrix operations on those vectors, give you an output embedding, and then you have this combination layer where all of that is combined for a translation task, or maybe like even if you have a prompt mixed into languages, your MoE model can do exactly what you meant, right? Even though your instruction was in two different languages. They also have this really nice visual. Actually, this is from the GLAM paper that I borrowed from. They give a pretty good idea of how to scale language models using the mixture of experts idea. So here you kind of send your input sequence in the English language through your tokenization scheme. Then you send it through the multi-head attention layer and add a norm layer. So till this point, it's the same standard transformer architecture. But right after this layer, instead of sending it to a FC layer, the output of this is sent to a gate, right? And this gate, and they do a pretty good job of visualizing it, this gate basically selects only 2 most relevant experts out of 64. So this is a 8x8 grid of experts, which means there are 64 FC layers, feed-forward networks, maybe of depth greater than 1. So there are 64 experts that are available in this GLAM model, and the gating layer is tasked with the job of only selecting 2. So the top K step in the GLAM architecture is a top 2 kind of function. So the gate is responsible for only selecting 2 out of 64. And once it selects the 2 out of 64 experts for each and every token, right? Like roses can break down into 2 tokens or maybe 1 token. It depends on your encoding scheme. So a word can be broken down into 1 or 2 tokens. Let's say that a word is broken down only to 1 token. So then each of the word, like a roses might go to this expert, R might go to this expert, and whatever is the output of the expert separately, it's added, it's concatenated, and then sent to the next addition and normalization step. And then the second block is the same as a standard transformer, nothing changes. So as you can see, right, like this is way more relatable to a standard transformer architecture with just one MLP layer replaced with an MoE layer. Right. In this, they are doing the routing at a token level, but if you check out this paper, they show how you can do routing even at a task level, right? Not just a token level. So I think I've covered all the visuals here, all these slides. I think I wanted to talk about this table, so I'm going to do that. I missed it. So in this table, this is taken from this paper, the LIMOE paper. I mean, this table just shows that a mixture of experts model does a better job in learning semantic information across modalities compared to two-tower architectures like Clip, Align, and Basic, right? So, I mean, actually, Basic does equally well, I mean, better than LIMOE, but you can see the parameters per token is much lower for LIMOE, which means it has a faster inference. So even though it does slightly better, LIMOE does faster inferences. And that's one of the key strengths of these MOE architectures. Because they are sparse, they run faster and they train faster. So this table basically establishes the fact that MOE architectures do a better job at learning multimodal data than the previous two-tower architectures that have been, popular. So I hope by now you, at a high level, have communicated a good idea about how mixture of experts and the gating thing operates. In the next few slides, I'm going to go a little bit theoretical to maybe solidify that intuition a lot more. So if there are any questions, you can pause. Otherwise, I'm going to continue.
One question. So the mixture of experts mainly act on the feed-forward layer and not on the attention part. Well, at least from these papers. So what I intuitively thought was the main barrier to the 1 million token thing was because of the attention. It kind of when you make the attention magic, it's like 1 million by 1 million, so much VRAM. So basically, the sparse mixture of experts by itself is not the solution to that 1 million context length, right?
Right. Yes.
Okay. Thank you.
Yeah, that's why in this paper also, right, we are not able to achieve 10 million context length. None of the papers except Gemini are able to achieve 10 million. So MOE alone is not the reason, but maybe the way, and again, the MOE is just a simple idea to replace an MLP layer with multiple MLP layers and then adding a gate before them. I think there can be some creative ideas in how you design an architecture with MOE layers. And maybe they have combined that idea with a lot of other innovations and achieved that 10 million goal. But none of the other papers that I've referenced, none of them are able to achieve the 10 million goal, 10 million context length.
Okay, so MOE is mainly good for faster training from what I can. Okay.
Faster training on larger data sets and even faster inference. And also MOE is really useful for multimodality, right? So that's what this kind of proves, that if you're training a multimodal foundation model, then you have a better likelihood of getting better benchmarks if you use MOE versus these dense transformer blocks.
Okay, one general question, but let's say you have two experts, right? Which is better, two experts or just making the parameters double, the original model?
Yeah, so all the data shows that it's better to have two experts than doubling the parameters of one expert.
Oh, this was on the same parameter level?
If you have the same parameters, then also I think the switch transformer paper, as per them, I don't know if I have a chart for it, but I think as per them, it's still better to use a MOE architecture for the same number of flops. So if you're running the same number of floating point operations at inference time, which basically equates to having the same number of parameters, it's better to choose a MOE design versus a non-MOE design.
Okay, gotcha. Thank you.
And I think just for reference, just for context, I think Gemini 1.5 Pro, I'm reading this saying in production is only going up to 1 million tokens. And then they add a sort of aside saying that in research, we've also successfully tested up to 10 million tokens, which I guess is what we're reading now. But I'm not sure if that's going to be used just now in production. But yeah.
No, that makes sense. So I think let's just now jump into theoretical details of the gate and how is the gate different from the traditional MLP layer. So in the traditional MLP layer, like whatever X input you have at the final layer, right? That's your response, right? Like there is no, in the absence of an MoE layer, whatever is the final encoding, you send it forward. But once you have an encoding layer, an MoE layer, what changes is you pass the embedding through a gate, and the gate for each of the experts right here, I goes from 1 to n, where n is the total number of experts in your architecture. Every gate gives you a vector embedding to vector embedding of equal size to the input embedding. And then once you take the dot product of that, let me correct myself. This G actually contains the importance or the selection score for a particular expert. So E here is the output of the gating network. So this is basically what you send to the gate. And here, this is the G vector, right? So the G vector that you see here, Gx of I, it's this thing, right? So you take the dot product of this column, which is like how much of the data you want to pass through each of the expert. You take this column and then take the original vector, and that becomes the response that you pass forward. So this is kind of the short equation to think about how MoE layer is different from just like passing the output forward. Each expert is a simple feed-forward neural network. This is common across all the papers. In all the papers, the expert is just a simple feed-forward neural network. Some have multiple hidden layers, some have only one. The trainable gating network, again, the gating network is also an FC layer with trainable parameters, which means at batch size, at training step 1, you start off with some initial values. And as you progress through the batches, the gating network also learns how to route which token to which expert. And all parts of the network, the gating network, the experts, the dense transformer blocks that appear before it or after it, all of them are jointly trained. This has been stated in all the papers. So, you don't separately train the experts or separately train the gating networks. Whatever your total architecture is, you train everything together. And it's also mentioned in the paper that, and again, the paper that I'm talking about when I talk about MoE is, it's this paper. Right? So this is the best resource for learning the MoE architecture, outrageously large neural networks, the sparsely gated mixture of experts layer. In that paper, they say that the gradients are backpropagated through the gating network to the transformer encoder that appears before it. And this is how it kind of works. I think I've covered this slide already. You will hear this term, especially if you're downloading Mistral models or any other MV models from Hugging Face or other places. You'll hear MoE4, MoE32, MoE256. This is basically just telling you how many experts does that model have. Now I go deeper into how the top key gating works, and the noisy top key gating is what has really changed the game. Almost all of the mixture of experts model use the noisy top key gating. None of them use the softmax gating. I mean, reason one is that this is not sparse, right? Even if you just use softmax gating, you will always have non-positive, some positive value or some positive, you'll have some positive score for sending a token to any of the experts, which means that all of the tokens that you get, that you send your gating, a softmax gating will say that every expert has some positive likelihood of accepting that token. So there's no sparsification, right? So basically, if you take one FC layer and multiply that by 256 and create 256 experts, the number of flops or floating point operations you need to do at inference time is not reducing, right? Like you're actually increasing it 256 times compared to a standard transformer architecture. If you basically send every token to every expert. So to solve that, in the paper that I just mentioned, they use this idea of keeping the top K scores only. So once you have the scores for every expert for a given token, you only select the top K, and the rest of the scores you change to -infinity, which after you apply softmax becomes 0. So your gating score, which is mentioned in this formula, your gating score basically goes down to 0 for many of the experts, right? So if your X is made of 100 tokens, many of the tokens in X, a token in X will only go to K of N experts. So if your MoE model has N experts in total, a token in X will only end up with K experts. So during inference time, there is a sparsification of the flops, right? Not all experts are being run on all the tokens. An expert is being run only on a fraction of the tokens that is sent to the gating layer. So I think that's really important to understand, because that's where the training efficiency and the inference time efficiency in MoE architectures kick in, right? Otherwise, they are no different. If you just use softmax gating, it's no different to dense transformer blocks. In addition, in the paper, they talk about this learnable noise parameter. So you do not just send you don't just send like the input embedding directly to the gating layer, but you multiply that by a FC layer, which is a noise layer. And these noise parameters are also learned. So in a way, as the training progresses through training step 1, 2, 3, 4, the model is able to make an opinion on how much noise it wants to add to every token before deciding which gate to send it through. And this kind of helps with one big problem that I'll talk about in the next section, which is balancing the expert utilization. Because what naturally happens is, like, even though you have 256 experts in your model, if in the initial training steps, 2 or 3 experts, the back propagation led to gradient shifts in only 2 to 3 experts, and they became really good at something, while the rest of the experts still had like lower weights. Those 3 experts will get most of the gradients in subsequent training steps. So then your experts will become unbalanced, right? And that's like a bad thing, right? So the noise helps in balancing the gradients across all the experts. And there are multiple few other tricks that I'll talk about. But this is like a very important component that you should add in your Torch training script or whatever when you're training an MoE model. So yeah, quick refresher, right? We have already completed everything on evaluation. We have completed basic introduction on MoE, talked about the gating structure. In the final part of the discussion, I'm going to talk about how do you balance the utilization of experts, especially as you scale these experts, to 25, 26, 300, 400. I think there was one question like, is MoE the sole reason that Gemini can scale to 1 million contexts? So for sure, it's not the sole reason, but then there are some really, one of the achievement of MoE architecture or training an MoE architecture is that it's really easy to shard a MoE model across multiple GPUs. Otherwise, all the current, like pre-MoE, all the other training routines that have been proposed, they only use data parallelism, which means you just copy your model across 10 or 20 GPUs, send different batches to every GPU, and then you average out the weights across all 10 GPUs. That's really the, I would say, coolest idea pre-MoE. But with MoE, what's possible now is that you can shard the experts. So if you have 256 experts and if you have 256 GPUs, you only keep one copy of the expert in every GPU. And that helps, that helps you to kind of reduce the training time and also train your entire architecture more effectively. So I'll go deeper into that, but like MoEs lend themselves really well in using many GPUs during the training phase. So I'll take a pause here, see if there are any questions, because I think the last part of the call is going to be just about balancing.
Yes, one slight question. So in the softmax stage, you mentioned, I can assume that basically that the token has like the highest probability it'll go to that expert, but from what you're describing, it seems like you kind of like multiply that token by a softmax and send to each of the experts?
Yes.
Okay.
Yeah, but only the top K.
Okay. So in the softmax scaling, basically all the experts get utilized for every single token. And for top K, like, okay, I see. Interesting. So kind of like the experts get like fractional tokens, kind of.
Exactly.
Okay, I see. Okay.
Good. So I think in the final part of this discussion, we are going to go deeper into the question that you just asked, or related to the question that you just asked. So the unique thing about MoE architecture is that every expert only observes a fraction of the input. No one expert actually sees the whole sequence of embedding vectors that are sent to the gate. And the job of the gate is to basically choose K out of the N experts. So naturally what's happening is, if you have a batch size of B, each of the expert receives, basically you are calculating the gradient on KB by N examples only, right? So, so every batch size is observed by K out of N of the experts, which means you're not calculating gradients on all the B examples, right? So even though you're sending all the B examples to the gate, only a fraction of the examples are being used for the gradient calculation. This makes the MoE implementation pretty inefficient because you have already loaded all the data into your GPU or TPU. And by the time it hits the gate, you're not utilizing, you're only sending like a fraction of the GPU cores, because at the next step, you're not sending the examples to every expert. You're only sending it to one of the experts while the data is still in memory, right? So that makes the MoE implementation a bit inefficient. The solution to this shrinking batch problem is to make the original batch size large, which is kind of the simplest way to solve it. But how does one do it? Like, that's a trick that they talk about in this in the MoE paper. So there's a particular trick in doing it, which introduces a new idea of using multiple GPUs for MoE architectures, and it's not applicable to the other dense architectures. So what I'm going to just talk about makes MoE specially scalable to many GPUs, and this idea cannot be applied to a dense architecture, like a non-MoE architecture. So in conventional distributed training setting, if you have a dense model, you need to copy the model to each of your GPUs. Then you can send separate batches to each of the GPU, calculate separate gradients, and whatever new parameters that you arrive at in each of the GPUs, those parameters are synchronized through a parameter server, right? Through a central server. Now, in the case of MoEs, what's possible is that you don't need to copy the same expert across each of the GPUs, right? Because the data that's selected for a particular expert need not be sent to any other expert, right? Which creates an opportunity to shard the shard the layers, which is like divide the layers across GPUs. And that's the thing that they do in the mixture of experts paper from the Google Brain team, which is they only make one copy of the expert on each device. This way, let's say that each device receives a batch size of B, right? And that batch size is multiplied by K by N, which is like the fraction of the batch that is observed by the model. And then you multiply that by the number of devices, right? So as you scale the number of devices in your training infra, you are solving the shrinking batch problem. So that's why MoE layers lend themselves really well in utilizing multiple GPUs if you have it, right? And they effectively utilize multiple GPUs because they are sharded, right? They are not like replicated, they are sharded. So you are using each of the GPUs very efficiently. And that's what makes the training, if you remember one of the original charts from the switch transformer paper, this is why the training is really efficient for MoE models. Because even at training step 1, you have run through larger batches through the MoE model and like each of the GPUs with only one expert in it has seen more variety almost, like, or has specialized on a particular domain of your input data, versus like a dense model. When it's replicated across devices, it's not able to effectively, you're basically, after you've trained the gradients on multiple GPUs, you have to go through that synchronization step, right? Which does not carry forward the learnings really well. But because the MoE is sharded, like, again, this is me trying to explain it at a vague level, but MoEs lend themselves really well in utilizing multiple GPUs. It solves the shrinking batch problem, and the more GPUs you have, the more effective your model is going to be at consuming larger and larger data sets. And you can imagine this is a problem for companies like Google and like such organizations. Like, they do have the GPUs available. They just need architectures that can lend themselves to utilizing all those TPUs or GPUs. So any questions here? This modern parallelism is a new idea that's only applicable to MoE layers, not applicable to standard layers. So I would say that's the key insight to take away from this slide.
Sorry, why isn't it applicable to standard layers again? Sorry.
Yeah, because you cannot shard a dense transformer, right? Let's say because a dense transformer, the requirement is you need to propagate the signal through all the neurons. Right? So you cannot shard it, right? Like you cannot divide the transformer into separate devices.
But can't you have the first device run the first part and the second device run the second part? I guess then you have to wait.
Yes,
exactly. Okay, I see. Yeah.
So this model parallelism, which is like parallelizing on the model, is possible with MoE layers. It becomes more apparent, like I think here. So this is taken from the MoE paper, which uses the MoE idea to scale vision understanding. You can see here what they do is they have the traditional VID dense transformer block. And after each VID block, they put an MoE block. And the MoE block, what happens is they replace the MLP MLP layer here with a sparse MoE layer. And then this sparse MoE layer, so till this point, all the layers, let's say if you have 10 GPUs or 10 devices, TPUs or whatever, AI accelerators, then all these layers are copied over to each of the devices. But once you get to the sparse MoE layer, you only make one copy of the expert on each of the device, right? And then once you get the input signal till this stage, it enters the router, and then the router decides, and the router is obviously copied over across devices. So there is a synchronization step. After every batch, the routers are synchronized across devices. So But once the signal crosses the router has already decided using the scores whether this token or whether this image should be kept on device 1 or it should be sent to device E, right? Because the router makes a decision which expert this token needs to be sent to. And if the answer is not this device, then there is a communication latency that it's added, because now that those tensors need to be sent through if the device is on the same motherboard, then it's sent to the same, it just goes via PCIe. If the device is on a different machine in the data center, then it goes via the network card. But that tensor needs to be now sent to a separate GPU, right? That leads to the sparsification, but also utilization. So one batch that goes through all of this, that batch itself is getting divided. So that batch which has traveled through all the network on device 1, it might continue to be on device 1, or it might need to be sent to another device when it reaches the MoE layer or the expert layer. And once the output has been created by the expert layer, again, it is sent to all devices for synchronization, and then you get the final embedding. So this is like a unique inter-device communication that needs to happen when you implement an MoE architecture, in contrast to the other layers, which are just copied over across devices. There are several advantages now to this, because there is only one set of experts, right? So even if you have, let's say, a sequence of sentences, the set of experts is the same. Even if you have 20 GPUs or 100 GPUs, you essentially have the same collection of experts. You can actually wait and calculate the output till the router layer across all your 100 GPUs, collect all of them together, and then send the rolled up tensor through the experts at once, right? That further solves the shrinking batch problem, because again, if you remember, right, the expert only looks at a fraction of the batch that is sent to it. So if till this point it has observed a batch size of B, an expert will only see a fraction of that batch. So the batch naturally shrinks when it arrives at the expert. But if we wait for multiple time steps of the input signal to complete till this point, we can send all the sequences at once through an expert, therefore increasing the batch size and again solving the shrinking batch problem. That's what they kind of talk about here. I think the goal of this slide is just for you to kind of take away that the inter-device communication, that dynamics changes a lot when you use an MoE architecture, and it gives some key advantages over dense architectures. This slide also kind of talks about the second impact of using an MoE architecture, which is now you need to manage inter-device communication, right? So if you have, let's say, 1,000 experts distributed across 10 GPUs, because there is only one copy of an expert in every GPU, every router, right, and a copy of the router is present in all of the GPUs. Like once you cross the router step, again, you need to decide where to send the tensor, right? And therefore, that's going to cost some device communication. Sometimes what can happen is there might be a token overflow situation where you might send the tokens to a device, but that device may not have enough memory left, which can create an error. And I'm sure everyone has experienced at some point your PyTorch training is going to crash. You don't want that. So to avoid that situation, researchers have come up with this idea of capacity factor, where what you do is like you set a cap on the batch size that is sent to every expert. So the batch size of data that is sent to every expert is the tokens per batch. So for a given batch, what is the total number of tokens? You divide it by the number of experts. So then basically it tells you the tokens that needs to be processed by every expert. And then you multiply it by a capacity factor. So if the capacity factor is 1.0, it means the RAM on the AI device is sufficient, right? It has no space for overflow, right? Like whatever tokens you are sending to the device, to that expert on that device, it only has memory available for it. But if the capacity factor is increased, then you're giving some, you're allowing for some space in some devices to deal with a token overflow situation. Again, this is more of like a practical thing to worry about. Has no impact on your training quality. But again, MoEs are really, really powerful when you have multiple GPUs to train on. Then it makes sense to be knowledgeable about this particular parameter. So that's that's kind of, I think now we're almost at the end of the discussion. Just another note on the network bandwidth part is, because you will end up there will be some cost in sending data from one GPU to another. There is another factor that that's talked about in the MoE papers, which is the computational efficiency factor. So this is the ratio of the computation done on a GPU divided by the network capacity of the GPU. So if you're sending more data to a GPU than the amount of data it can, the operations it's doing on that data, then that's going to slow down your MoE training. You don't want that, right? You want the computation on the data to be of more flops or more operations than the rate at which it can consume the data. So for GPUs, this ratio is always 1000s to 1, because GPUs are known for having, thousands or even sometimes millions of cores, and they can do a lot of floating point operations at once. So in this particular paper, they use one hidden layer as an expert, and it's just a simple trick to think about, and it gives you some intuition about what's the computational efficiency of your expert. So if your expert is just one hidden layer, then your GPU is processing input size into hidden size, and hidden size into output size number of operations, right? Because once your input tensor arrives, that's the number of floating point operations you do. And then from hidden size to output size, that's the additional number of floating point operations you do. So the ratio of computation is basically you add both of this. So which is like input size into hidden size into input size plus output size divided by the input size. So yeah. So basically the longer the greater the number of your hidden, the greater the number of the nodes in your hidden layer, the more computationally efficient your expert is. So just keep that in mind again when you're designing MoE architectures. So I think that takes care of all the sharding and how to utilize multiple GPUs when training MoE models. The last part is how to make sure that your expert training doesn't become imbalanced. And multiple papers have talked about this, that it has been observed that the gating network tends to converge to a state where it always produces large weights for the same few experts. So even if you have 256 experts, the same 10 experts are being used for all your batches. And this imbalance has like a positive feedback loop, or it's self-reinforcing, because if only few of the 256 experts have gradients that increase its weight, every subsequent batch will give a non-zero gradient for those experts, and only those will be continued to use. So to avoid this situation, in the MoE paper by Bengio et al., they talk about adding this loss term, the L importance term. And what this does is it comes up with this idea of the importance of an expert. And the importance of an expert is just the sum of the gate values for that expert. So if you remember, so, if you sum up these gate values, that becomes your importance of this expert. And once you have that importance, then you calculate a loss term, which is nothing but the variation of the importance value across the experts. So then this loss term incentivizes the trainable gate to assign to ensure that the sum of importances for each of the experts across all the observed tokens is more or less the same, right? So it's not that all of the tokens just go to one expert while the other experts see nothing. So to avoid that, the Bengio et al. Paper talks about adding this loss term to whatever trainability you have. And that helps with balancing expert utilization. So that basically ends the expert discussion. This is the final slide I think that I have. This is just to prove a point that MoEs, like if you have larger data sets and if you have many GPUs available, it makes much more sense for you to train an MoE model than a dense transformer model. Here they show that if you train an MoE model on 100 billion words, then the perplexity, right, as a function of model parameters, right? So you have the same number of parameters for the same MoE model. When it is trained on 10 billion words, the perplexity is around 55. But if the same MoE model with, let's take this example with 1 billion parameters. So if a MoE model with 1 billion parameters is trained on 10 billion words or 100 billion words, the perplexity reduces significantly, right? So this basically proves that MoE models do a better job at consuming more training data, or they have higher learning capacity. They don't just train faster, which we showed in the switch transformer visualization. They also train much more effectively on larger data sets. So with that, I think we have arrived at the end. If there's any questions, leftover questions, I can take those here. Otherwise, we're going to wrap up the meeting.
Thanks for the meeting. One final question. So is like mixture of experts in general, like always better in like language modeling setting?
Yes. I would say if you have the GPU devices, it makes most sense. Like especially if you want to train a model on multiple GPUs, a mixture of experts would be really, really useful. And this actually just happened today. I would really recommend everyone to check out this repo. So Jeremy Howard just tweeted maybe 10 hours back, there is this new GitHub library that's been open sourced called FSDP and QLoRa. And this now allows, it will allow you to shard, basically do a mixture of expert training where you can shard your model to 2 or more GPUs, like even desktop GPUs that you have available, right? So if you have more than one GPU, then just use this FSDP library and train your model, like your language model, your vision model, or if you're training a multimodal model, right? In all 3 cases, you should utilize the MoE architecture.
Okay, thank you.